Beautiful.
Okay, so Natasha now is going to talk about from speed space to neural correlates, quantum mechanical principles of alien navigation. So,
yes. Okay. Hi everyone. Thank you so much for being here. I'm really excited to have learned from all of you and to continue learning from all of you, and also to share with you the story of the quantum birds. So, the first time I really truly spoke about the birds, the first time that I did justice to the birds with my words, my friend Helena and I were sitting on this beautiful fire escape, which was the fire escape of my house at the time. And from the very moment that this conversation began to the very end, there was a gray pigeon perched right here on the gutter, obsidian orbs of eyes staring down at us, I kid you not, for the entirety of the conversation. Entonces, as we awaken new gods with technology, we are responsible for remembering the old. As we construct these electromagnetic entities with reduced reflections of ourselves, let us truly reckon with the forces we want guiding the spirits of these silicon beings. Which sets of intentions we want shaping the informational signature in the fields of our collective? Do we want trickster, god of chaos, whose direction has no aim, whose cause has no side, leading the way, trickster, lover of chaos, disruptor, joker? Do we want those building these machines devoted to Ares, god of war, fed by conflict, Mars incarnate? What if instead, as we play with these modern manifestations of the power of fire that cooks our food, the fire responsible for the low entropic growth of the human part of our brain, we turn our attention to the goddess of the hearth, Hestia, to goddess of wisdom, strategy, and yes, still war, Athena, for guidance? What if we ask the Tao to light our torch and guide our way? We see that when we do this, when we recall the sheer power of our biological bodies, our carbon vessels of cosmic source energy, the head of the snake meets its tail, and we end right back up at the frontiers of modern science. From all-pervading unities, prana, brahma, chi, we find ourselves swimming in the infinite universal quantum fields. As we speak of the mysteries of consciousness, of sentience, perhaps we may cease attempting to skirt nature and rather recall, remember, and embrace her principles encoded and embedded in ancient behavior that has captivated philosophers, scientists, and people, humans, for millennia. Aristotle once remarked on the astonishingly precise migration of cranes from the steppes of Scythia to the headwaters of the marshes of the Nile each and every year. We now know that when collective behavior exhibits such spatial precision and temporal consistency, there is indication of an orchestration of coherence at foundational scales of being, the physicalities composing every instance of existence. For what are we? What is nature? Mother Earth and all of her creatures, but carbon-based configurations of overlapping waves of electrons and protons and photons at play. The electronic bodies of birds have been around for 66 million years, and they've been traversing the skies bird-like creatures have been traversing the skies for around 150 million years. A journey guided by the very entity which guides our own compasses, the churning torus of Earth's magnetic field. Okay, so how do these birds actually migrate across the Earth and the globe from these very particularly and precise locations of rivers and marshes the same place every year? Well, it has to do with quantum mechanics. Okay, so we have a bird. This is a pigeon. Pigeons are awesome. They've been used in dozens of bird experiments across multiple decades. And this blue guy right here, this arrow, is a blue photon. So a blue photon comes in and it hits the bird's eye, travels into the eye, and it hits the retina. And when it hits the retina, something really interesting happens. So this is our retina. Both our retina, bird retinas, they pretty much look the same. And we have this blue photon that comes in and it's traveling through all of the various rods and cones and photoreceptor cells. And when we get here to the cellular level, scattered throughout all of the cells on this all of the cells in the retina is a protein called cryptochrome. Cryptochrome literally means color carrier, which means it can absorb color, photons, different wave packets of light, and do various things. Now, these cryptochromes are scattered both throughout all of these cells in the retina of birds and in other places of the body. We care about the retina for now. So, when the blue photon comes in and it hits the cryptochrome protein, what it does is it hits two different molecules in the cryptochrome protein, flavin adenine dinucleotide, or FAD, H, and tryptophan. So, as we dive into the quantum mechanics, and this is going to be like a mini crash course on quantum mechanics, so actually before we do that, can we just get like a hand raise of who here has some sort of physics or quantum background? Okay, fantastic, thank you so much. Okay, so what we care about is what's going on there, when the blue photon hits the molecule. Okay. So, what happens when the blue photon hits the molecule, flavin adenine dinucleotide, or FAD, is something called the radical pair mechanism. Because scattered across all of these molecules are nuclei and electrons coupled to the nuclei. And what can happen is you can have a pair of free radicals, or free electrons, and they interact with each other. And they interact with each other in a way that is entangled. And I say entangled, and maybe that's a buzzword. What does it actually mean? It means that the information that is encoded in these electronic objects, which, again, quantum mechanics is our most precise way of describing how these things are, instead of like, proton one here, electron here, da 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 da. It's waves of probability that interact with each other at this fundamental scale. So what actually happens? There's something called the hyperfine interaction, which is where we can talk about the dynamics of the dynamics of fundamental particles change when they're coupled to each other, and we'll get into the specifics of that. So again, we're following this blue photon. Remember, it comes into the eye, hits the retina. The retina has proteins, cryptochrome, and inside cryptochrome are these molecules. Amazing. So, what you see here is a diagram of the radical pair mechanism, and this is really the core of the process and where the magic happens. So we have this blue photon, and we're dealing with two electrons here. Two electrons coupled to a nucleus, okay? So who here has been told of and remembers something called the Pauli exclusion principle? We got one hand, couple hands, raise them high if you've heard, please, so I can see. Okay, beautiful. So thank you. So just as a refresher, the Pauli exclusion principle says that if you have two electrons orbiting a nucleus, they have to have different spins, right? And we're gonna get into exactly what spin is later, but for now, just consider it a property of the wave function that describes these fundamental particles. So the two electrons that are doing the signaling in this bird's eye are originally in something called the singlet state, which means that they're in the same orbital, so the same distance from the nucleus, but one is spin up and one is spin down. Now, what happens when the blue photon comes into the molecule, the electrons, is that it excites one of the electrons in this pair. And so we follow the blue photon up the diagram, and we see that one of the electrons, which is on the Fad molecule, suddenly becomes excited enough to jump over to tryptophan, the other molecule involved in this reaction. And now, first we started like this, right? Spin up, spin down. Now a blue photon has come in and it has excited one of the electrons. So the Pauli exclusion principle no longer applies. This electron can flip here. This electron can flip here. They can be both spin down, they can be both spin up, they can be spin up, spin down. It doesn't really matter because they're in different orbitals. And this is particularly useful and particularly important because of something called the hyperfine interaction. So when electrons or any particles for this matter are coupled to a nucleus, and in this case, molecules are full of nuclei and full of electrons. So we have these two electrons coupled to a nucleus, and the nucleus begins to act like the sun, and the electrons the earth. And the electronic states start oscillating around the state of the nucleus. And because we're in an excited state where the spins can flip back and forth, what we see is that in around a period of 10 to 100 nanoseconds, depending on the actual configuration of the system, these spin states of these electrons flip back and forth. Now, something really important about different spin states is that they have different energy levels. And in chemistry, whether it's biochemistry or any chemistry, different energy levels lead to different reactions. Okay? So if we, and at the end of this at the end of this 1 microsecond, because something called the chemical recombination rate, or the amount of time in which the electrons need to make a decision about which state they're in so that the biochemistry can continue, is about 1 microsecond, or 1 times 10 to the minus 6 seconds. So when this happens, if the electrons are in a singlet state, it's going to produce different chemistry than if the electrons are in a triplet state. Okay? So why is this important, and what the hell does the Earth's magnetic field have to do with it? Something called the Zeeman effect. In this process of interconversion in these 10 to 100 nanoseconds before the 1 microsecond time is up, the strength and direction of the Earth's magnetic field directly modulates the rate at which this interconversion happens, which means that the strength and direction of the Earth's magnetic field directly modulates the chemistry that is happening in the bird's eye. Okay? So, something that we do need to go over to understand this process fully is quantum mechanical spin. Now, if you've ever taken a quantum course, you'll probably hear your professor say, spin is an abstract thing and it's impossible for us to understand. I just think that's not true. It's really it's a barrier to entry that is there for no reason. So we're going to go over it today. At its basic level, spin is an informational signature, a property of this quantum particle that encodes for how representation of the particle changes as you rotate it in space-time. Now, I'd love for you guys to draw your attention to these 3 footballs, or soccer balls for my Americans in the room over here, and take a look at what spin looks like visualized. So we start in this green and red state, right? And the color has absolutely nothing to do with spatio-temporal dynamics, right? It's a state of the ball. Now, when you rotate it 360 degrees, or 2 pi radians in space-time, we don't end up back at the green and red situation. We have this blue situation. We need to rotate the ball twice fully in space-time in order for it to come back to its original representation. This is called spin 1/2, because after 1 rotation, we're halfway back to where we started. And this guy is exactly what we see with electrons. So I'm gonna put some some information up here, and it might be a lot for the eyes, but we're going to go through it. An example of this in actual quantum mechanics is the wave function of the hydrogen atom. So you guys have probably seen this picture before, right? The hydrogen orbitals? Okay, amazing. So all this is the representation of the wave function, again, which describes the probabilities of existence of these particles, which I have written out for you here. Psi is like the classic letter that we use. And it's made up of radial part, which is R, a angular momentum part, which is Y, and then crucially a spin component, which is chi. And this chi part of the function is what we see in this ball. Everything else is encoded here. This guy doesn't encode for spin. The spin is encoded in the ball. So the way that this ball spins, the electron spins, that is what is getting modulated by the strength and direction of the Earth's magnetic field. Okay? Okay. Before we move on, does anyone have any questions? Can I clarify anything for you guys? Okay. And as a disclaimer, the following slides have a lot of math. Okay, so in my bachelor's thesis, oh, did you have a question?
Yeah, I just have a question. You said chemistry, what's going on during the transduction in the eye depends on the Earth's magnetic field.
Yes.
And that, I'm guessing it's something to do with the relative orientation of the spin, of the electron spin, and the Earth's magnetic field.
Mm-hmm.
That doesn't necessarily give the bird away to systematically respond to the Earth's magnetic field unless the orientation of the molecule is controlled, right? Like
Sorry.
if you have a bunch of molecules facing in all directions, it's not surprising a priori that the chemistry would be affected by the magnetic field for each molecule.
Yes.
Each molecule is pointing in a random direction.
Mm-hmm.
So it doesn't, that wouldn't feel like the tissue is actually using the magnetic field. It's not really controlled.
Are you, to clarify, your question is that the plane of the molecule itself is, they're all random, and so when the Earth's field interacts with it, the plane, the direction, yes, the planes of the molecules are altered, but what gets signaled, what gets transmitted from the quantum information to the classical, chemical, and then electrical information, it doesn't really have much to do with the orientation of the molecule. The spin itself isn't dependent on the orientation of the molecule. The spin itself is describing how the wave function of each of these electrons changes as we rotate it fully in space and time. And so if we're making a full rotation of these electrons, it doesn't matter if it's pointed X, Y, or Z, because at the end of the day, we're coming back to its original state. Does that clarify your question?
Not necessarily, but maybe the following slides will.
I think so. I hope so. Yes?
One question, maybe it's me, but the electromagnetic field of the Earth changes depending on the time, and depending on the position, or whatever other variables. How does this affect the reaction? Because depending on the time we are measuring, it will have different effects. No?
You mean the polarity of the field? Or the strength of, okay.
Strength of the field, or
See, the strength of the field does vary, but we're interested in orders of magnitude, and the order of magnitude of the field doesn't vary too much. Okay, so you'll see in the math why the order does not vary, or why the order doesn't. The order of magnitude is what we care about. Okay. So, quantum biology is a highly controversial and contested field. If you've ever delved into this topic, you've probably heard of the classic complaint of hot, wet, and noisy. Biological systems are governed, dominated, dictated by thermal noise. There's absolutely no way that quantum effects could have any relevance to biology. hear you, have been there, have to say, I think we need to think a little bit deeper. We need to really ask ourselves whether the laws that govern every single fiber of existence, not just in our bodies, but in the entire universe, has nothing to do with how we function. So let's prove it. Okay, the first thing we need to do in order to prove that quantum effects are viable in biology is compare timescales and energy scales. And in quantum mechanics, oftentimes these are the same thing. So on the left, you have the frequency of omega, the angular frequency of Earth's magnetic field, and these are just like a bunch of constants with numbers that I will not repeat for the sake of your ears. And what we find at the end of the calculations when we plug in around 50 microteslas, which is the strength of the Earth's field, so or so, give or take, is that the field oscillations are about 1.4 megahertz. Now, this guy, the S hat Z, that's the spin operator. And what we see is that it is directly related to h bar, which is Planck's constant, 10 to the minus 34, forgetting the units right now, times m, the scalar of spin. And the delta E's that we see are the changes in energy due to whatever variations we're dealing with. In this case, it's going to be the Zeeman effect, which just applies quantum Hamiltonians are very similar to classical Hamiltonians. They're linear operators. And so when you place an electron or any particle in the magnetic field, you have to add the frequency of the field. And so multiplied by h bar to be at the quantum scale. So what we see is that the change in energy due to the field is directly related to its frequency. And what we need to care about is whether this guy is on par with the degree of coupling of the electron to the nucleus, right? And when we do the ratios, I think the hyperfine interaction, which is the coupling to the nucleus, is around 10 to 34 megahertz. So we see that these two magnitudes come to about 10 to the minus 1 or 1 over 10. And this is fine. This is excellent because remember the hyperfine interaction, the coupling to the nucleus, is driving this oscillation of spin states, and the Earth's magnetic field, the Zeeman effect, is simply modulating it. Okay? So this 10 to the minus 1 is very good for proceeding with the calculation. And then we construct a Hamiltonian. So this first Hamiltonian is, the first part, the sum, is the coupling of the electrons to all the possible spin states. Now, and the second term is the Zeeman effect of these two spin states with the two electrons. Now, remember, we're in a molecule. It's really busy in a molecule. We got a bajillion nuclei and even more electrons. So how do we deal with this in a way that allows us to actually do a calculation that is not going to take a quantum chemistry computer and that I can turn my thesis in by April? At the brilliant suggestion of my advisor on this project, Bill Bialik, he suggested that we, instead of going through all of the biochemistry of the various molecules and being super specific, we approximate the interactions with the nuclear spin states to random Gaussian fields. And you might be like, how can we do that? Well, think about it. There are so many different nuclei that we can pay attention to that it's really, really hard to know which electrons these guys are actually coupled to. So, okay, amazing. Okay, so not only is this great for those of us who are doing the computations, it also sets the scene of this mechanism being viable in general biological conditions. Okay? Not just in the bird's eye, but in any given biological situation. That is huge. Okay, now, there's some more math. What you really need to pay attention to is this yellow box at the end. Remember back when we were in the retina, what we care about is the chemistry, because those are the signals that get translated to chemical and then electrical information for the bird to actually perceive and navigate. So what we do is we take the Hamiltonian from the previous slide and calculate what is called the singlet yield probability, which is the fraction of electrons in the singlet state after multiple rounds of this electrochemical reaction. And what we get out is this phi s, which is the singlet yield probability, which sums over all the possible spin states. And p is the singlet state projection operator, so it's just like, okay, we're looking for the electrons only in this state. And then this f is in the equation above, and it comes from this integral definition. Okay, so knowing this, we wanted to see what happens when we plug in values of k and omega that are biologically relevant. So what do we get? These are two plots that show the singlet yield as a function of the ratio of Earth's magnetic field energy scale to the hyperfine nuclear coupling scale. And can you guys see the y-axis here? Is it too small? You can see? Okay, amazing. So the first graph looks for a variety of k's, and the reason we care about a variety of k's is for a variety of electrochemical reactions, even though we do have a pretty good estimate of how they relate to omega and h. And what we see is almost a dip of 1/3 in the singlet yield calculation when we apply, the k of 10 is like way too long, way too fast, the quantum effects will be relevant, but in the biologically relevant regime, which is the k equals 1, 0.1, and 0.01, and again, this is like compared to the omega and h, we see a significant dip in the singlet yield, which means that the Earth's magnetic field, that magnitude of field, is altering the chemistry of what happens in this bird. And then the second plot, I think, is really nice. You can see the dip a lot more clearly. And instead of altering the k value, or the chemical reaction rate, we alter, this actually goes to your question about the orientation, because this graph shows what happens when the fields act on different components. And so if we're interested in different orientations, then seeing what happens when the field acts on all the various components, whether it's x, y, or z, we get the same result. The only thing that doesn't have a result is when it acts purely on the z direction, because it's the component of the spin operator that is in the Hamiltonian that is being affected by the field. So we need it to act on, if it acts on the z direction, it also needs to act on the x and y. Yes?
What is the biophysically relevant scale that you're mentioning?
Okay. So remember that the chemical reaction happens at a rate of 1 microsecond, and the alteration of these fields at the quantum mechanical level, or the oscillations, are from 10 to 100 nanoseconds. And so we need a k that is, we need the k to be longer than omega. So we need the rate to be like 0.1 of omega over h. And so that's why the biophysically relevant scales are k equals 1, 0.1, and 0.01, because it's a slower rate than the rate of the field, omega and h.
And is there an interpretation spatially in terms of physical space? Is there, I want to understand this kind of effect and what parts of the molecule could be affected. On the entire molecule, on the cell level, or?
So let me go back a few slides. So if you turn your attention to this guy, the molecules need to be like close, like basically next to each other.
Yeah.
And does it affect the whole cell? Kind of. It affects it's in the cryptochrome protein, and so the aggregation of this effect in the cryptochrome protein is thought to have like effects. If this is the retina, it's connected to the optic nerve, and so this aggregation of the small scale spatially adds up in the protein, and then the proteins are scattered throughout all of these guys.
So if I understand correct, this actually was a question I wanted to make again, but maybe since we're here, there is an underlying assumption, and maybe also goes in the direction of your question. But the underlying assumption is that you want to demonstrate that quantum fluctuations can have a real impact. And the underlying assumption is that if it has any impact at a biological relevant scale, even if it's small, we assume that this eventually can go up the scale and influence behavior. But that's an assumption that, like, what you want to demonstrate is the first level.
Yes.
Then the fact that this first level triggers an effect on the level of the entire cell, and then maybe visual perception, and then maybe go direct to behavior. That's
yes. It will. The next slides after will definitely answer this question.
Okay.
And of course, it's a fabulous question, and we do actually need to bridge some of the gaps still between specifically the cellular and protein level with the more macro scale effects. But the macro scale effects are astonishing. Maybe we'll go to those.
Thank you.
Okay, so we've gotten past the mathy slides, and now we're here. Okay, so this is a bit of a precursor to Giovanni's question, and very, very simply, this is what we've done. We have shown that the hot, wet, and noisy complaint comes from trying to compare energy and timescales of classical information with energy and timescales of quantum information. And what we've done is show that the interactions that happen in the quantum energy scales at the quantum timescales can affect what happens at the classical measurement. And then we are assuming based on more macro scale evidence that the classical measurements, the aggregation of them is a result of the aggregation of the quantum information in a rhythm, in a song, if you will. And so it's not that each individual quantum event is, I don't know, like changing the state of the bird from 50 million light years away, but it's that the rhythm, the accumulation of these quantum events is what leads to a change in the classical signal. So how do we know? How do we know? There are 3-4 beautiful studies that have been done on trying to answer this exact question. The first one is what we really want to pay attention to is a region or cluster of the avian brain called cluster N. So back in the 90s, this research really took off, and one of the first main findings is that there is an explicit functional connection between cryptochrome expressing neurons in the retina and cluster N, which I have labeled in yellow here. And this is the first piece of evidence of a direct informational pathway between these cryptochrome expressing neurons and regions of the brain that are relevant for vision. Number 2, when these regions were legion, the birds could not navigate with a magnetic compass. They could only use the sun and stars. And number 3, and shout out Klaus and Alex for teaching us about this in the masters, we can extract tuning curves of single neurons that encode for the strength, direction, and polarity of the Earth's field. And so this is a computational neuroscience conference retreat. So these are the most direct pieces of evidence of neuroscientific evidence that this bridge between the quantum scale that, again, we still need to work on from the cellular and protein level is relevant at the macro scale. And then, okay, cool. These are for birds, but what does this mean for us? Specifically, humans also have the cryptochrome protein in our eyes and in other places in our bodies, and they're also magnetically sensitive. I've put a bibliography, if you can go to reference 35 if you want to read this study. And we don't obviously need to migrate with the Earth's magnetic field, But it is thought that back in the day when we would go hunting and gathering and like walk for 24 hours a day, we had a magnetic sense, we had this orientation, but because we live in the modern age, we don't need it anymore. And number two, there was this beautiful study done at Caltech that put humans in a Faraday cage, which is a cage that blocks out all electromagnetic signals, and then they applied a micro-Tesla field, the strength and direction of the Earth, or the strength of the Earth's magnetic field, and there was a predictable change in alpha waves when this field was applied. So these are the specific implications regarding cryptochrome and Earth's magnetic field orders of magnitude. Now, generally, what have we done? We've shown, this is a skeleton of the diagram from a couple slides back, a physiologically viable way for quantum information to be relevant at a classical level. Again, the birds are a specific example of a very beautiful general mechanism. And this can be applied to anything. I took this diagram from one of Stuart Hameroff's papers, one of the most infamous and controversial quantum consciousness researchers, because this mechanism is what's being proposed in microtubules and neurons, just in another way, in another fashion. Same mechanism, same time scale, same energy scale argument, just a different system. And finally, who here has tried infrared therapy, or like put your face in front of an infrared light before? Yes? One person? Okay. 2 people? Okay. So like, infrared light is thought to help with inflammation and all this good stuff, but why? How? What? There's no like solid answer on this. But perhaps the radical pair mechanism can offer some type of explanation, right? Remember, we followed the blue photon on this guy's path throughout the bird's eye, and this blue photon activated a very specific process. So who's to say that other wavelengths of photons can't activate different processes in different parts of the body at this quantum mechanical level? It's something to think about. So finally, thank you to Professor William Bialik for guiding me on this journey, and the Princeton Physics Department. This was my senior thesis. Thank you to UPF, CBC, Gustavo Deco for continuing this research, and shout out to IONS. Thank you to IONS, the Institute of Noetic Sciences, for drafting me to apply these methods to systems in brain. And thank you guys for listening.
Any questions?
So there was talk about macroscopic things happening in the bird's brain as being quantum, as being related to sort of these quantum effects you're talking about. From what I took from the slides from the talk, wouldn't it be a fair summary to say that this amounts to adding an extra sensor to a pigeon's brain? The brain is still completely classical. We don't need any kind of quantum description of the information processing properties of the brain. You just added another sensor, namely some kind of magnetic field sensor, whose description is the finest level of any quantum mechanics. But the sensor, basically, its job is to sense the magnetic field and to produce something in the brain that depends on that, so that the brain can use it to make decisions and guide behavior. But there's no indication that anything after that is really inherently quantum. Like if the magnetic field causes sort of more of one molecule to be produced than the other, then it seems like after that point, you don't really need to think quantum anymore. It's just like, neuroscientists are used to thinking of, okay, one molecule produces more than the other, and then there are some molecular transduction processes that translate that into a different decision. I'm never convinced that we need to think quantum at all after that point.
Really?
The detector, it sounds like it's very, we need quantum mechanics to describe the interaction between the magnetic field and these producing molecules. But after that, I feel like, can't we just go back to what we're doing? Let's do quantum.
Yes, exactly.
Okay.
Yes, exactly. Thank you. Yeah, it's exactly this. It's that we're not making the claim that the quantum information is changing other parts of the classical system, but rather the quantum information is underlying the signals that get propagated throughout the classical system.
In the same way that we have retinas and photo transduction at its sort of fundamental level is going to be quantum. You won't be able to describe the absorption of a photon in a photoreceptor without quantum mechanics, and that's something we all sort of accept, right? We don't think of vision as quantum, though.
Yes. And the radical pair mechanism is indicating that we can't account for certain effects without explicitly considering quantum mechanisms. Yes? Okay. Can you like, is there something explicitly that is, like, do you have a question specifically regarding the transduction of the information? Like, it sounds like there's something more?
Yeah, if we're running out of time, we could take this offline. But the idea being that there's different levels of abstraction. And in neuroscience, you think of circuits, you think of information processing, and mostly it's classical thinking. Nobody doubts that if you go lower, if you start talking about neurons, individual molecules, atoms, electrons, you need quantum mechanical sort of ideas to describe those systems with perfect precision. But the question is whether those kinds of ideas actually really need to be used at higher levels. Can't we just think of circuits and classical information processing? That's kind of what it's.
We absolutely can. However, we do need to consider the quantum components that are creating the signals that get propagated throughout the classical circuits. Does that clarify?
Yeah, yes. Let's maybe take it offline.
Okay. Other questions? Yes.
Yeah, so it's, thank you for the talk. So it's related to this interaction between quantum information and classical information. So, can you give an example? So you were referring to the Turing curves.
Mm-hmm.
So maybe it's related to the previous question. So what's the contribution here of this quantum interpretation into that?
Absolutely. Okay, let's go back to this guy. So the field and the electron and the proton, they're doing their thing in this microsecond, right? And then the cryptochrome protein, which is the space in which this is occurring, is located in the retina, which is connected to the optic nerve. And so the actual process of how the quantum information gets translated to classical is through a series of measurements. And these measurements are energetic states of signaling molecules. And the energetic states of the signaling molecules, that's chemical information. This chemical information is proposed to travel through the cells in the retina and then gets converted at a junction at the optic nerve. And those signals, those electrical signals, get sent down the optic nerve and then processed by the brain.
What is information here? It's information about what?
Mm-hmm.
No?
Yes, like the exact chemistry, the exact chemical products that are getting produced.
I meant more like how is this representing stimuli? When you were talking about Turing curves at the end, right?
Ah.
Yeah, I don't know what is.
Yes. Okay.
So about neurocoding.
Yes. Okay. So how the quantum information
How is
was.
this shaping?
Okay. So that hasn't actually been explicitly studied. As the Turing curves themselves, I would imagine that the neurons that are encoding for Turing curves also have these proteins, something similar. It doesn't have to be cryptochrome, could be something else. And either the same mechanism occurs directly in these neurons, or they're connected to the neurons in the retina that are propagating the information. That's an excellent question. Does that answer those? Oh.
Any
Yeah, I have many questions just. So on the tuning curve, what is on the x-axis? Just the strength of the magnetic field, like the intensity.
So there are three different types of curves that, like, some neurons encode for the strength, some the polarization, and some for the angle. the direction.
Okay, so the idea is this is not just, so because I was thinking more like a compass, so this is just like, you know, the magnetic field gives the bird a compass, but you're saying it's more than that. So you can really, I mean, does the bird know where the bird is on the kind of on the sphere?
Yeah.
Is that possible from these sensors or?
So okay, wait, hold on. I think it does act like a compass, and then
So it just tells you where the north is, basically. That's it.
and
So that's a good ingredient for navigation, but it doesn't really explain how the birds would find something that is 5,000 kilometers away. Right?
the idea is that because cluster N is in the occipital areas, that they actually literally see the field.
Mm-hmm.
And so it's an overlay. And how they go from the exact spatial precision, well, the field itself is quite precise to various locations, right? Like even the aurora borealis, like that's a direct example of how the field changes like very, very explicitly in very short spatial scales.
It's like another sensory feature.
But it's also extremely small, right? I mean, it's extremely small and also variable somehow.
The field? Yes. So the variability, we care about order of magnitude here. So like regardless of whether it's like it ranges between like 45 to 67, I think. And like I put in 50 microteslas in this simulation and tested it for the same range, but what we really care about is that 10 to the minus 6 or the microtesla, and it regardless of like how it's oscillating, it still produces this shift in the singlet field calculation.
Yeah, last question, maybe. No.
The only sensor for magnetic field that they have, because long ago, I don't know what's the state of the art now because I'm totally ignorant of the field. So I heard about something like just on top of the beam with iron or something like that. I can't remember exactly what it was.
Magnetite. Yeah, so this great question. So this was proposed to be how they sense the field. Magnetite are like iron magnetic particles in the beak, and during the experiments where they like the same ones here, where they like put the bird in a cage and then altered the field and then see how it flew. The alteration of the field didn't change when, or the bird's navigation didn't change whether they had the magnetite particles or not. They like genetically coded the bird and it did in or out, and it didn't matter.
What are the heat molecules doing there?
Magnetite? I think maybe it's used to help with food selection. But most of the discussion's been in the context of the navigation, so I'll have to look into it further for what the actual function is.
Okay, so thanks, Natasha.
Thank you.